So, now how do we determine whether the reaction will go to the product side or to the reactant side? Suppose in the beginning or in the initial condition, or I, we have 2 molar of A, we have 1 molar of B, we have 4 molar of C, and we have 2 molar of D. How do we determine whether the product is being formed or whether the reactant is being formed? For this, we recognize another parameter that we call the Q. So in this case, QC. If we have the data of KC, then we have to use the QC. Now, the way we calculate the QC is exactly the same with the way we calculate the KC. So QC is C power to the second, and D, and then A power to the second, or squared, and then B. So in this case, we can immediately calculate that we have 4 squared, and then multiplied by 2, and then this one, 2 squared, multiplied by 1. So in this case, I believe you will get 8 or so, yeah? Please check the calculation. So from this on, we have to compare the QC and the KC. If the QC is exactly the same with the KC, that means we already reached the equilibrium. This is the equilibrium condition where the reaction macroscopically does not occur anymore. So this is the composition where it reaches the equilibrium and it will stay there. However, if the QC is smaller than KC, this means that when this is smaller, this means that the reactant overcomes the product. So this part is way too big. That's why the Q is being very small. Because the reactant is way too big or way too much, the reaction will occur to the right. So it will form products. On the other hand, of course, we have also reaction that occurs to the left or to the reactant side, and this will be achieved when the QC is bigger than KC. If the QC is bigger than KC, that means we have too many products. This value is way too large, and therefore, these excess amount of products will shift and forming the reactants to be able to achieve the equilibrium. So suppose in this case we have a QC of 8, and then the KC, let's just take again imaginary number, so 4. Yeah. So from here we can compare the Q and the K, and we can say that QC is bigger than KC. That means in this reaction it will occur to the left or forming the reactants. So now we will complete the ICF table. However, because it's not final situation, but instead equilibrium situation, we call this the ICE table, with the E means the equilibrium state. So as usual, we will do this based on stoichiometric chapter that we have discussed before. However, as I mentioned, there is no such thing as limiting reactant in an equilibrium reaction. So instead, we just assume everything based on their stoichiometric coefficient. So in this case, we have A, we assume it to be X. And don't forget, because the coefficient is 2, we have to write down 2X. For B, X is sufficient. For C, because the coefficient is also 2, we write down 2X as well. And for D, it is X as well. Now, note that before we have determined that the QC is bigger than KC, meaning that the reaction will occur to the left. So the reactant will be formed and the product will be consumed, so it will be negative like this. So by the equilibrium, we will get 2 plus 2x, 1 plus x, 4 minus 2x, and 2 minus x. And we can use this composition and the K to find the X. So again, Kc should be equal to the concentration of C power to the second or squared multiplied by concentration of D divided by concentration of A squared and then concentration of B. So Kc in this case is equal to 4 2x squared 2 minus x divided by 2 plus 2x squared and then 1 plus x. So using your math knowledge that you have studied in mathematics, we can find the x. In this case, the equation will be power to the third divided by this one, and then the k will be 4. So at the end, you have to transform this equation into this form. So x plus blah 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 x squared plus blah 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 x and plus a constant equal to 0. And then it is advisable for you to use your calculator and solve the x1, x2, and x3. So it will be easier. Or if this is a simpler equation like quadratic equation, then you can use the quadratic formula to find the square roots. In this case, you have to find the cubic roots. You can also use calculator for this, and please learn how to do this in your calculator. And therefore, you will get x1, x2, and x3. So what do you do with these three values of x? Which one will you choose? Okay. Now, of course, the main idea here is to never get a negative value here. So everything here is in molarity. So this is 2 plus 2x molar. This is 4 minus 2x molar. So in this case, you cannot have x bigger than 2. If the x is bigger than 2, then that means 2 minus 2 will be 0. And in this case, you will always have some number, some positive number over here. So be careful in choosing the x. Make sure that none of these numbers will become negative or become 0, and that is the x that you are going to choose. So therefore, if you have solved the x, and then you can say that the equilibrium composition is as follows. So the equilibrium composition. Now, just for the sake of calculation, let's say that the x that we got is 1, for instance. We have 1 as the x. So we can say that at the equilibrium, we have the concentration of A being 2 plus 2 multiplied by 1. So 4. Concentration of B will be 1 plus 1. So 2. Don't forget the unit. This is molar. This is also molar. Then concentration of C will be 4 minus 2 multiplied by x, so 1. So this is 2 as well. And then D will be 2 minus 1, which is 1 molar. So this will be the composition at the equilibrium. And you can compare this. In the beginning, you have 2, 1, 4, 2. But at the equilibrium, actually, this will become 4, 2, 2, and 1. So be careful in determining the square roots or the cubic roots over here. And then after you find the correct value of x, you have to substitute the x over here, over here, over there, and over there. And then you can find the equilibrium composition that corresponds to the k value for this reaction. So you see here that we are talking about Kc. However, the very same principle will also apply to Kp. Just for Kp, you will use the partial pressure of D divided by partial pressure of B. And you also have Qp, and if Qp is smaller than Kp, that means the reaction occurs to the right. And if the Qp is bigger than Kp, that means the reactions will occur to the left. So the same principles will apply, but you just take the ones in the gas phase. In this case, you take aqueous and gas for Kc. And for Kp, you only take the gas phase.